Welcome to the deep dive. So our mission here is pretty straightforward. Cut through all the noise, sift through the latest stuff, and get you the vital insights. Quickly, thoroughly. Today we're diving into something, well, genuinely innovative. It's a new breakthrough in taking carbon dioxide, CO2, that greenhouse gas we hear so much about, and actually turning it into useful products. And this really gets over a major hurdle, making the reactors, the machines that do this conversion, stable enough to actually use commercially. So, yeah, let's get into it.
Exactly. And what's really significant here for you listening is just the ambition behind it all. I mean, turning CO2, a pollutant messing with our climate, into something valuable. That's a huge scientific goal, a huge environmental one, too. So any tech that helps us do that effectively is, well, incredibly important. And historically, the big problem, the real Achilles heel for these kinds of CO2 conversion systems, it's always been stability. They just didn't last.
Okay, so let's break down the technology itself a bit. We're talking about something called electrochemical CO2 reduction. People often shorten it to CO2RR. Basically, it's a green tech. It uses electricity, and ideally that's renewable electricity, right, to change CO2 from the air into useful materials, things like carbon monoxide or ethylene, even alcohols. And these aren't just like lab experiments. They're actual building blocks for fuels for industry. It's literally turning pollution into a resource. But yeah, what was stopping it?
Right. The practical use has been really held back by this poor stability. And the core issue, the frustrating thing, was this buildup of potassium bicarbonate salts. If you picture the inside of the reactor, these salts would literally crystallize and just gum up the works right in the gas flow channels.
How does that happen?
Well, you have potassium ions, and they move through this special filter inside called an anion exchange membrane over to where the reaction happens at the cathode. And there, under the right conditions, high pH specifically, they react with the CO2. And the result, this salt precipitates out, it blocks the CO2 from getting where it needs to go, and it floods another key part, the gas diffusion electrode. That's where the gas and the electricity meet for the reaction.
Ah, okay.
Yeah, so as Haoshin Wang, one of the key researchers, put it quite directly, salt precipitation blocks CO2 transport and floods the gas diffusion electrode, which leads to performance failure. And this wasn't like years down the line. This failure often happened within just a few hundred hours. It's nowhere near good enough for commercial use, It's like trying to run a factory machine that breaks down every week.
Yeah, that sounds like a real bottleneck, all this potential, just stumbling because of salt. So what did the researchers down at Rice University figure out? How did they tackle this?
Well, it's one of those solutions that sounds almost surprisingly simple once you hear it. Instead of using plain water to humidify the CO2 gas before it goes into the reactor, they pass the gas through a weak acid solution first.
Acid. Okay. How does that help?
So this acid-humidified CO2 method, it's kind of brilliant in its subtlety. Tiny trace amounts of vapor from these acids. They've tried things like hydrochloric acid, formic acid, acetic acid, pretty common stuff. These vapors get carried along with the CO2 into the reaction chamber. And that just slightly changes the local chemistry right where it matters. The key thing, the real insight, was that the salts formed with these acids are way, way more soluble than that troublesome potassium bicarbonate.
So they dissolve instead of building up. Exactly.
It prevents them from crystallizing out and clogging those channels. Xiaoyun Hao, another lead on the project, explained it really well. He said, we hypothesized and confirmed that acid vapor could dissolve the salt and convert the low-solubility KHCO3 into salt with higher solubility, thus shifting the solubility balance just enough to avoid clogging without affecting catalyst performance. Simple shift, big effect.
So did it work? I mean, did this subtle chemical tweak actually make a big difference in practice?
Oh, it made a huge difference, a dramatic difference, really. The numbers are quite striking. Get this. The system's operating life was extended by more than 50 times.
50? Wow.
Yeah, 50 times. So in their lab device, using a standard silver catalyst as just a common material used to help the reaction along, converting CO2 to carbon monoxide, they got stable operation for over 2,000 hours.
Okay, 2,000 hours versus a few hundred before. That's already massive.
Right. But then they scaled it up. In a larger 100 square centimeter electrolyzer, more like something you'd actually use, they hit over 4,500 hours of stable performance. That's a major milestone for the whole field.
4,500 hours.
Compare that to the old way, the standard water humidification. Those systems typically failed after only about 80 hours because the salt just choked them.
80 hours versus 4,500, that's night and day.
It really is. And they could actually see it. They built these special reactors with transparent plates. With the old method, You could see salt crystals forming within like 48 hours. But with the acid-humidified gas, no significant buildup even after hundreds of hours. And if any tiny deposits did form, they just dissolved and got washed away. It's like the reactor could suddenly clean itself.
That's incredible. And it wasn't just for one specific setup, right? You mentioned versatility. They showed it worked with different catalysts, like zinc oxide, copper oxide, things that make different products from the CO2.
That's right. It wasn't tied to just one specific reaction pathway. It worked across multiple catalyst types, targeting different valuable products. And crucially, it was compatible with the standard membranes and materials already used in these systems. They found very little corrosion or damage, even to sensitive parts like the anion exchange membrane, because the acid concentrations they used were so low.
So you don't need to completely rebuild everything to use this fix.
Exactly, which is huge. This work really opens the door to making CO2 electrolyzers that are much more durable, much more scalable.
Yeah.
And that's absolutely critical if we ever want to see this technology used widely, at industrial scales as part of serious carbon capture and utilization strategies, moves it from interesting research towards potentially viable industry.
And the beauty of it seems to be the practicality, the accessibility. You're saying it's just small tweaks to how they already humidify the gas, not some expensive, complex new component.
Pretty much.
Yeah.
That's the elegance of it. No major redesigns, no significant added costs. Ahmad El-Ghazar, another author on this study, summed it up nicely. He said, "Our method addresses a long-standing obstacle with a low-cost, easily implementable solution. It's a step toward making carbon utilization technologies more commercially viable and more sustainable." It's a great reminder, really, that sometimes the best solutions come from understanding the fundamentals, the basic chemistry, even in these really advanced systems.
So we're wrapping this deep dive up. The core takeaway seems pretty clear. A really clever, maybe even simple adjustment, understanding that solubility issue, can lead to just massive improvements. It can turn a technology that was, well, kind of fragile into something robust and potentially game-changing. It really shows that big impacts don't always need massive, complicated changes. Sometimes it's about finding that crucial, subtle shift.
Absolutely. And it really gets you thinking, doesn't it? If just trace amounts of a common acid can unlock this much potential in a green technology, what other small adjustments might be out there waiting to revolutionize how we tackle other complex problems? Like, how could thinking about things like local chemistry or solubility balances, these sort of fundamental interactions, how could that spark solutions in totally different fields, maybe even outside of engineering, something to ponder?